So I'm going to really quickly jump us through all of our linear regression stuff. We've covered our normal distribution and z-scores last time. So we're looking at correlation coefficients and nonlinear transformations. We will have one thing that's relatively new this time around on residuals, which will come up in the homework a little bit. So correlation is a measure of how well two variables relate to one another. If you have a positive relationship, so that's a positive correlation coefficient or positive R, that means as one variable increases, in general the other variable increases. So these two would be positive correlations. This would be a zero correlation where I'm not necessarily going up or down in general. These would all be negative correlations on bottom. Okay, then I've got a positive correlation with an outlier on this side. If you square your correlation coefficient, you'll end up with a measure of strength. So if your R squared ends up being between 0.6 and 1, do it this way. 0.6 is less than x. Then you have a strong relationship. If you are between 0.4 and 0.6, or at them, then you've got a moderate relationship. And if you've got a value that is below 0.4, you've got a weak relationship. Just because two variables always happen together doesn't mean that one variable causes the other to happen. It's possible to have a third outside variable that causes your relationship. Our textbook example was murder and ice cream sales. If there was a correlation between murder and ice cream sales, it would likely be due to an outside variable rather than murder causing ice cream sales to increase or ice cream sales causing murder to increase. It could be something outside like temperature or seasons. Generally, people buy more ice cream in the summertime. Generally, people are more outside and together in the summertime, which has more opportunity for murder. It also tends to be hotter outside, where people tend to be more aggressive when it's hot. So it's quite possible there's a third outside variable there. Last time we created a best fitting line, and we did that by getting all of our observed values here in blue, and getting the difference between what was observed and what was expected here in red, and then trying to minimize that distance. And we had a formula that we used in order to do it, which we did once by hand. And it took us the whole class period to go by hand, so I'm not going to do it again. But since you guys will have calculators on your final exam and won't have to do this by hand, what you're really doing, though, is you're minimizing the difference between every observed value and your expected value in order to get the best possible best fitting line. Once you know what the slope and the average of your distribution is for the best possible best fitting line and the average of your x and y on your sample, then you can use that to get a correlation coefficient using this formula. So your slope is equal to your correlation coefficient times your sample standard deviation of y divided by your sample standard deviation of x. If you want to do it with a calculator, you can create two lists and then calculate your linear regression. If you just need to find a best fitting line, then you can skip straight to your linear regression t-test. That'll give you your best possible linear function and the probability of getting a linear function with that slope if the actual correlation is 0, which is your p-value. So in this case, once you get your linear regression t-test, your t-score that you have here represents the number of standard deviations away from average. Your p-score is the probability that this could happen randomly if there was no correlation. Degrees of freedom, the more degrees of freedom you have, the closer to an actual bell shape that you'll be. If you have more than 30 degrees of freedom, then you've basically got a bell curve, and you can do a z-test instead of a t-test. I'm not going to worry about that for this class. But later on, if you go into AP Stat, you'll have to worry about how many degrees of freedom you have. Generally, the more degrees of freedom you have, the better. the more values that you have in your distribution total, the higher your degrees of freedom are. So if you've got 2 variables, your degrees of freedom would be the total amount of values that you have minus 2. If you had 3, it would be the total amount of values you have minus 3. A is your y-intercept, B is your slope, S is your standard deviation, sample standard deviation, and R squared is your strength, R is your correlation. So from this, we could say that we have a positive because our correlation is positive, strong because our R squared is above 0.6, linear because we used a line relationship between X and Y. Okay, if we do want to convert those, we can take our linear function, y equals mx plus b, and change either y to ln y or x to ln x, or both, to get different types of functions. If we change the y to be an ln y, then by taking the, raising both sides to a base of e, we'll end up with an exponential function. If you take the natural log of x, you'll end up with a logarithmic function. And if you take the natural log of both, you'll end up with a power function. So that allows us to have different types of functions that we could fit a best fitting line to by changing our y to ln y or changing our x to ln x. The reason why that's important is so that we can do a linear regression t-test with our transformed values and get a p-value. How probable is it that this correlation could exist if there was actually no correlation? So how probable is it that we would randomly get a correlation this extreme if our actual correlation is 0? Okay. And I also need to talk about residuals. Residuals are a measure of how much error that we have in a model. So if I made my best fitting line for this a linear function, oops, not drawing. There we go. We made our best fitting line a linear function. Actually looks something more like this. There we go. The difference between the observed value and the expected value is what's called my residual. So I've got a lot of distance right now above my best fitting line. You can see I've got negative residuals for the next 4 points, negative residuals, and then positive residuals for the last 2. If you are not given enough information to know what R squared is, and you want to test to see whether this is a good model or not, you can look at your residuals. If you have a pattern to your residuals, in this case I've got a general curve. My residuals are in a curved shape. That tells me that there's a better model than the one I chose. So in this case this is a linear model. Because our residuals are curved, I know there's a better fit somewhere. Here's another model. This is an exponential model because it took the log of y. You can see my residuals still have a shape of a curve. So this is still not the best model there is. Okay, if I go to model 3, I don't have a general shape here. We're not all curved. I kind of go up and down. So that tells me this is a fairly good model in order to represent our data with a logarithmic model. And if you check our r's, you'll find that that's also the highest r squared. So 0.99, 0.97, 0.94, my highest r squared would have been from model 3, which was the only one that didn't have a pattern to its residuals. So patterns to your residuals could be something like having all of your residuals above the line, or below the line, which just means we don't have a very good fit. Or it could mean that we have a curved pattern to our residuals, either curving up or curving down. Both of those mean there's a better model. Okay, so let's try a couple examples. Okay, so what I have here are the distance of a bunch of planets to the sun. Along their semi-major axis. So this is their distance at their largest point, at their largest distance to the sun. I also have the period. That's the time it takes to complete one full rotation. So you can see Earth's. We are about 150 million kilometers from the sun. That's from the center of the Earth to the center of the sun. And we rotate around the sun once every 365.26 days. That extra 0.26 days is the reason why we have a leap year. That extra day makes up for the 0.26 extra days that we have when we revolve around the sun. Okay, so I'm going to try to use nonlinear regression to see if I can find a relationship between the distance to the sun and the orbital period of an object rotating around the sun. Let's go Aileen. In our calculators, if I want to do a linear regression t-test with this data, what's the first thing that I would have to do? Okay. I'm maxed out in volume, but is there any way that you could turn up your microphone? Okay, I can hear you. So what's the first thing we need to do? Okay, so I'm going to go ahead and type our data into a list first. Okay, after I type all of this data to the list, then I'm going to need to test a bunch of different models to the data. So those are all of our distances for the sun, and then I've got our orbital periods here. Three, two. Okay, so now that I've got all the data in the calculator, I'm going to go ahead and turn diagnostics on. That gives us more information about our correlation coefficients whenever we fit to a model. Okay, so I'm going to test linear, quadratic, cubic, and logarithmic exponential power, and we'll see what our best relationship is to the data. So if we do a linear function, here I've got our linear best fit and our R squared. Aileen, back to you. Is this a positive or negative correlation? Okay, this is a positive correlation because R is positive. Is it strong, moderate, or weak? Strong. Okay, so I'm going to copy down this R squared, and we'll see if that's our strongest relationship to the data. So we had... model in R squared will tell us whether this is the strongest. Our linear model had an R squared of about 0.97. Okay, so I'm going to quickly go through and we'll check our other models. Quadratic. Next up is Jana. Jana, looking at this quadratic model, is it a better fit or not as good of a fit as our linear model? Better fit. How do you know? Okay, our R squared was 0.9997, so we know we don't have to use this linear model now. Okay, I'm going to keep going. So a cubic. Okay, Kelly, is this a better fit or not as good of a fit as our quadratic model? Better? Okay, so cubic is better. I've got 4 nines now. 1, 2, 3, 4, and a 7. Okay. And logarithmic is worse. Exponential also worse. 0.789. I guess don't know those lines. And the last one, a power function. So next on my list, Kenichi. Is this power function our best fit, or is the cubic function our best fit? Okay, I've lost Kenichi, so I'm going to jump to Aileen. Aileen, is the power function our best fit, or the cubic function? Power. Okay, so power function is our best fit at 0.12345 and then a 7. Okay, so before I move on from this, I'm going to take a look at the power function that we just created. So this is y equals a x raised to the b power. Right now our y is our period and our x is our distance, since that was list 1 and list 2. We had y equals a x raised to the b power, where a was some constant. I'm not going to care about what a is right now, but I am going to look closely at what b is. B is 1.5. So this is really the distance to the sun is equal to some constant a. Oops, sorry. Y first, our period is equal to some constant a times our distance to the sun raised to the 1.5 power. If I raise something to the 1.5 power, that's the same thing as the distance raised to the 3/2 power. Okay, and then if I square both sides, that'll give me my period squared is equal to some constant squared times our distance cubed, which means that the orbital period squared is directly proportional to our distance cubed, which in physics is known as Kepler's third law of planetary motion. Okay, Jenna, over to you. What do I need to do next in order to get a p-value? Jenna, are you with us? Okay. So we've got our strength. We know the strongest correlation to the data is now a power function. What do I have to do next in order to get a p-value? Okay, anyone? What do I have to do to get a p-value? So the probability that this could happen randomly. I can see Kelly's mic flipping, but I can't hear her. So I'm going to do a linear regression t-test. My problem here, though, is right now this is x and this is y. So I'm not actually aligned if I'm a power function. Does anyone remember if I have a power function, how can I transform that power function back to a linear function? Do I need to take the log of x, the log of y, or the log of both? Log of both, perfect. So if I make a table really quick, transformations for linear, do nothing because you're already aligned. For logarithmic, take the log of x. For exponential, take the log of y. And for a power function, take the log of both. Log x and log y. Okay. So we are power functions. That means we need to take the natural log of both x and y. So I'm going to go into list 3, scroll up to the name, hit enter, and we can type in a formula. So this is the natural log of list 1. So now list 3 is ln x. I'm also going to go over to list 4, scroll up to the name, hit enter, and type this as the natural log of list 2. So that's natural log of y is now list 4. Okay, that will allow us to do a linear regression t-test. So now if I hit stats, tests, linear regression t-tests, because we've undone our power function to create a line with list 3, that's the natural log of x, and list 4, the natural log of y, as our axes, we can get a p-value. Okay, you can see our p-value is pretty extreme. We are 994 standard deviations above average. So the probability that our actual correlation is 0 and we would randomly get these results is really, really small. 1.17 times 10 to the negative 21st power. Okay. Let me go ahead and graph really quick since I'm already here. I'm going to hit stat calculate our power regression one more time so that that's stored in our calculator. Since whatever regression test we did last time is what will be stored. Okay, that uses list 1 and list 2, so this is x and y is our best fitting power regression formula. Then I'm going to hit y equals, variables, statistics, equation, regression equation, and that will paste the last equation that we did. If I hit second stat plot and turn our first plot on, so graphing list 1 and list 2, then I can zoom to our statistics, and you can see all of our points, and in black our best fitting line. All of these ones that were just filled in, that means the observed value was exactly our prediction. All of these ones that are not filled in means the observed value was slightly more or slightly less than our prediction. But we could use that to make predictions. So if I wanted to calculate if there was a planet that was exactly 100 million kilometers from the sun, how long would it take to orbit? I can hit second calculate a value at 100. So if x is 100 million kilometers, then it would take about 199.96 days to orbit around the sun. Okay, so looking at our data and going down the line again, I believe we're on Kelly next. Kelly, what is the correlation between x and y? So is it... Okay, go for it. Okay, so that's my correlation coefficient. What's the strength, linearity, and slope of our correlation? So strength first. Is it strong, moderate, or weak? Strong. Is it positive or negative? Positive. And then what's the linearity? What model did we use? Power. Okay, so we have a strong, positive relationship to a power function. Or we could say there is a strong positive power relationship between x and y. And we actually went a step further earlier, and we're able to prove that our period squared is proportional to our distance cubed. So that would mean y squared is directly proportional to x cubed. Okay, we used a power model. And our equation for that model is y equals ax raised to the b, where a was around 0.199 and b was 1.50. Okay, r squared. Okay, over to Sarah. Sarah, what does this r squared actually mean? So if we said there's this really strong relationship between the planets and their periods, what does that mean? Okay, I've got nothing from Sarah. Kenichi's still muted, so I've got Aileen. What does it mean when I say there's a strong relationship between the planet's distance to the sun and their period? Okay, I'm going to go back. If we have a perfectly strong correlation, then everything is in a pattern. Everything is in a line or in a curve. The weaker our correlation gets, the more spread out our points are around our predicted line. So the stronger that our correlation is, the more predictable our results will be, which means the better fit that our model is to the data. So in this case, because there's such a strong relationship between the planetary distance and their periods, we can be confident that our predictions will be more accurate. So something like that. Okay, Jana, I'm gonna go to you. So our p-value for our best fitting model, if I go back, which again is our transformed model, since we have to transform back into a line, so that's lists 3 and 4, is here at 1.17 by 10 to the negative 21st. What does that actually tell us? What does it mean? That what would occur? Okay, so the probability that if there was no correlation between, in this case, planetary distance to the sun and the orbital period, we could still get results as extreme as we observed. Okay, so the probability is extremely low that this could happen by random chance. Okay, Kelly. We have a dwarf planet named Ares, which is slightly more massive than Pluto and has a distance from the sun of 14,410 million kilometers. How could I figure out what the expected orbital period would be using our model? Zoom out a little bit. So the question is, what would the orbital period of Ares be if our model was okay for that data range? What would I have to do? Perfect. So right now, because I've got our best fitting model as y1 right now, I can plug that in like this. So variables, y variables function y1, and I'm going to plug in the value 14,410. Gives me an orbital period of 346,684.4 days. So that's how long it would take to revolve around the sun. Okay, going back to Aileen. Unfortunately, it's not okay to predict the orbital period of Ares using our model. Can you tell me why? 10,440. So why is it not okay to use our power model to predict the orbital period of Ares? I'll give you a hint. It has something to do with the range of values in our data set that we use to construct our model. Okay, I'm going to open to anyone. Why is it that it's not okay to use our power model to figure out what the time it takes Ares to revolve around the sun is, even though it is okay for all of these other planets? Yes. So our range of values that we use to construct our model were between 58 million kilometers away from the sun and 900 million kilometers away from the sun. So because this value is outside of our data range that we use to build our model, we don't have any evidence to say that the model will continue. I know some of you might be in physics and you're going to yell at me because this model does actually apply to Ares, but if you were to keep going further out, so to the point where the next star over, so the closest star to us, Andromeda, started to have an effect, then this wouldn't be true anymore. There would be other outside variables that were affecting the motion of the planets, and we wouldn't be revolving with this period. In fact, we wouldn't be orbiting at all. Okay, any questions on anything? All right. I'm going to stop there. You have 14 questions that are multiple choice, which I'm going to throw up for homework up on WeChat. Okay, I'm going to look to take these by, we'll say Tuesday of next week at midnight. Because they're multiple choice, I can't tell you whether your answer is right or wrong, but I can answer any general questions that you have about these. If you need more help, I've got examples in the probability packet. As well as the previous tests from last year that I've already linked on WeChat, actually. Okay, thank you guys for coming. I hope you guys have a good weekend, and I will see you next week. Goodbye.